Okay, good morning, everyone, and welcome to the public talk section. And today it is our honor to have David Mota with us. David Mota, he is a professor at the Institute of Theoretical Astrophysics, University of Oslo. And today he will tell us about dark matter or gravity beyond general relativity. Without further ado, I will give the stage to you.
Okay, thank you very much. Good morning, everyone. Thank you for attending the public talk. I hope, so I was supposed to give a talk for the really general public. So I've upgraded a little bit the level. It's still general public, but at least you should know what is Newton's law of gravity. That's the only requirement here. So I'll go for that. So I'm going to talk about dark matter or gravity beyond general relativity. So in order to describe the universe, cosmologists basically have two main theoretical pillars to explain what we are observing. And the idea, of course, in cosmology is to do the observations, be able to explain, to understand what are the laws that are behind the creation, evolution, and maybe the end of the universe. And these two pillars basically are, one, to describe the standard model of particle physics, which is to describe matter there is in the universe. And basically the standard model of particle physics says that there are a finite set of particles in the universe. Basically, they can be classified in quarks, which will form the protons and the neutrons, that hopefully you know that. And then we have other particles called leptons, which are, for instance, the electron, from which a proton and electron can form an atom that we are made of. And then we have the forces of nature. So this model is extremely good, was tested up to very high precision. And so physicists believe it's true, you know, and we see the matter, we do the experiments in particle physics accelerators. So, thank you. So this is a very good pillar to basically, that we can use to explain what we observe in our universe. Now, matter lives in a given region of space and at a given region of time, at a given moment of time. And that means we also need to be able to describe what is space and what is time. And that nowadays is, we use the mathematical formalism called general relativity. So general relativity was proposed by Einstein in 1915, more or less, the beginning of the 20th century. And for Einstein, general relativity, space-time is not a fixed framework, it's something that in fact has its own dynamic. So space and time, they change, they oscillate. So you can think of space-time as like a fluid that surrounds us. So in order to describe the universe, cosmologists nowadays, they use general relativity to describe space and time, and they use the standard model of particle physics to describe what is the matter that we observe there. The problem arises because when we, as physicists, try to describe what we observe in the universe. Okay, I just saw some known physicists coming to the audience. Oh, that's a pity. I'm very sorry. I changed my talk. I thought it was only physicists. Oh, gosh. I'm sorry. So I will have to continue on this one now. I'm sorry about that. So we have a problem because we cannot, in fact, describe what we observe in the universe using general relativity and using the standard model of particle physics. And one thing that we need is the so-called dark matter, and I will tell you what it is. But basically, if we look at the universe at very large scales, and even from large scales, I mean from galaxy scales all the way to the edge of the universe, we need this very strange component, which we call dark matter, that we don't know what it is. It's not part of the standard model of particle physics, but we need it to explain many observations that we see in the universe. And I will give you some examples of what it is. So, if we can't explain what we observe in the universe, then it means something is wrong with our theoretical framework. The mathematical equations that we use to describe our universe, they must be wrong. Because we can't explain what we see. And, sorry, there was something that jumped. They must be wrong. So the idea as a physicist is to try to find out where we got it wrong. And usually the alternative, since we have these two main theoretical frameworks to describe what we see, maybe it could be that general relativity is wrong, or maybe the standard model of particle physics is wrong. So the standard model of particle physics being wrong, it means the standard model of particle physics does not describe all the particles that exist in the universe. Maybe there is an extra particle, maybe the dark matter particle, that is not described by the standard model. Or maybe there is no such a particle, and the equations that we use to describe space-time, those are the ones which are wrong. Okay, so this was the general introduction. Let me now tell you why we believe there is some dark matter component out there in the universe. I start a little bit before, in the 1800s. So in the 1800s, astronomers noticed that the planet Uranus did not follow the expected Kepler law. So if the astronomers would apply Newton's second law of gravity to describe the orbits of the planets, in the 1800s they found out that Uranus was following a very strange orbit in the solar system. So they wonder, well, maybe Newton's law of gravity is wrong, the one that we use, that the force basically is proportional to the masses and inversely proportional to the distance square. So could Newton's law of gravity be wrong? Well, they were wondering about that because it worked very well for all the other planets in general, even for physics that you do here on Earth. But when you try to describe Uranus, that didn't work out well. So people start to wondering, well, maybe there is some strange matter out there, some other, for instance, a planet that we can't see, some dark planet at that region, which is changing Uranus' orbit. Or maybe it's just Newton's law of gravity that is wrong, and we need to upgrade Newton's law of gravity. So in the 1800s, Verbier and Adams, they have proposed that there is in fact a new planet out there, which, although we cannot see, maybe dark for the moment, the planet is there. So they have said, no, we should trust Newton's law of gravity because it works very well everywhere that we know. We do lots of tests and Newton's law of gravity is perfect. So there should be really a planet there. And the planet, they call it Neptune. And they say to the astronomers, hey, just keep looking there and you will find the planet in this position with its orbit. And what was remarkable is that in 1846, they found that planet. They found Neptune at the predicted orbit, predicted position by John Adams and Verbier. So Newton's law of gravity was correct. We didn't need to change the law of gravity. We just could not see this dark planet, which is not dark at all. It's just Neptune. We couldn't just see with our telescopes at that time. Okay? So the new planet was in fact the explanation for this strange mystery that we had in our solar system. So something very funny happened because a bit later, also Verbier noticed that Mercury's perihelion was also not following what we expected from Newton's law of gravity. Mercury's perihelion was shifting, and the shift on the orbit did not correspond, again, what Newton's law of gravity was predicting. So Verbier says, well, there must be also a planet out there that astronomers haven't detected yet. Just like Neptune, Verbier says, no, there must be a planet out there. The planet is called Vulcan. You just don't see it. Newton's law of gravity is perfect, is there. Just keep looking for Vulcan. And, well, as you all know, I hope, there is no such a planet as Vulcan there. Yes? People never found one. What people found out many, many years later is that Newton's law of gravity is not a perfect law of gravity, is not the full description of gravity, and in fact you have to upgrade Newton's law of gravity to general relativity. And so when Einstein proposed general relativity in the beginning of 20th century, then we could explain very accurately Mercury's perihelion. Okay? So in that moment, there was no such a thing as a dark planet near Mercury. What happened is that our law of gravity, that the one that we used, was in fact wrong. So let's fast forward a little bit in time, and let's take a look of what happened in cosmology nowadays. We start first looking at our solar system. So in our solar system, this is the solar system, what we have basically, we have that most of the mass of the solar system is in our star, the sun. 98.5% of the mass of the solar system is in our center, in the sun. And then we have all the other planets rotating around. Yeah? So if we use Newton's second law to describe the rotation curve or the orbits of the planets in our solar system, and assuming that most of the mass is in the sun, then we can see that the force, the acceleration that these planets will feel, the force, the attractive force, gravitational force that these planets will feel, should decay with the distance. So Mercury should feel a very strong force, a very strong acceleration, while Pluto, up there, should feel a much lower force, so much slower acceleration. And that means if I'm going to plot the velocity, the orbital velocity of the planets over its distance from the sun, we have that Mercury is a planet which moves at higher velocities. That's natural because the force is really strong, so the acceleration is very strong. And as we go to the outskirts of the solar system, the velocity decreases with the distance. So Pluto is the slowest planet in our solar system. Well, now to tell the truth, I'm not sure if Pluto is a planet anymore. But that's the idea. And the whole reason for that, the reason why we see these planet rotation curves, that's the name of this curve here, is that all the mass of the sun, all the mass of the solar system is basically the sun. So the mass is in the center, all the mass, and basically so the force decays with the distance square. So this guy's like that. Now, astronomers have decided we like to measure velocities in our universe of things. So astronomers decide also to measure what are the velocities of stars in a galaxy. So they look at a galaxy. A galaxy is an object made of many stars. And they also will apply Newton's law of gravity, which, let me just tell you, Newton's law of gravity works very well here. It's like saying general relativity, because in these regimes, general relativity recovers Newton's law of gravity. So that's the same thing, basically. Okay? So if we apply Newton's law of gravity to a galaxy, we also can see that most of the mass of a galaxy usually is in the center of the galaxy. There's a big bulge in the center of the galaxy, so there's usually a supermassive black hole in the center of the galaxy, and most of the stars are going to be in the center of the galaxy. And some stars, of course, as we go to the outskirts, there'll be less and less stars. So the amount of mass decreases as well. A little bit like in a solar system. Yes? So what that means is that stars in the bulge of the galaxy, in the center of the galaxy, they should move really, really fast. And that's because most of the mass is there. They're closer to the center of the galaxy, so the acceleration is very fast, so stars in the galaxy should move really fast. As we go to the outskirts, these stars, which is outside at the edge of the galaxy, they should move slower and slower because the acceleration basically decreases as the distance square. So astronomers thought that they expected when they're going to measure the velocity of stars in galaxies, and they would do the same plot, so velocity in the y-axis and the distance on the x-axis, they would expect that in the center of the galaxy, stars which are in the center, they would move very fast, and as they measure the stars which are in the edge of the galaxy, these stars would move slower and slower. What they found was quite surprising, is that when they measured the velocity of the stars at the edge of the galaxies, they moved as fast as the galaxies in the center. So the velocity of the stars did not really decay as we predicted, as we expected. That's the red line, that's what we expected. Velocity of the stars, they kept constant. So even the stars which are at the edge of the galaxy, they move really, really fast as the stars that they are in the center. And in fact, when astronomers nowadays, they measure molecules of hydrogen which live completely outside the galaxy, these molecules of hydrogen, they move as fast, in fact, as molecules of hydrogen that live in the center of the galaxy. So even outside the galaxy, there seems to have a very strong acceleration, a very strong force, even outside the galaxy. So this was discovered in the particular galaxy rotation curves by Vera Rubin. She discovered this in the 1950s. Of course, this brings the question, if we look at our law of gravity, if the force goes with the mass divided by the distance square, that the gravitational attraction is not decreasing with the distance from the center, because the force here is as strong as the force in the center. And if that's the case, it means that the only options is that there must be some kind of mass, that not all the mass is here, but there must be some mass also outside the galaxy. And this mass that we cannot see, that's what we called dark matter. So it's a mass that there must be in the outskirts of the galaxy. So astronomers, that's one of the first ways that astronomers found out the evidence that there must be some dark matter particle, very massive particle, that must surround galaxies. We cannot see that, that's why we call it dark, but it must be very massive and should create these halos around our galaxies. So the galaxies are really small, they're just a few kiloparsec, and the dark matter halos are several hundred kiloparsecs. So it's a huge halo. So as you can see when you look at this picture, this is just an artist's representation, of course. The galaxy, a star in the center of the galaxy or a star at the edge of the galaxy, it feels the same amount of mass because the mass is everywhere. So it doesn't matter. That's why we don't see a decrease on the galaxy rotation curves. There's dark matter everywhere, there's mass everywhere. And even if I have a hydrogen molecule moving here, it also feels the dark matter halo gravitational attraction, so it will keep moving very fast. So that's a very strong evidence for dark matter, and this is not the only one. We have strong evidence for dark matter in many different ways. So the question that astronomers ask then is dark matter the only explanation for this phenomena? Is it possible that there is no other explanation to explain why the velocity of stars keep increasing and molecules keep increasing even outside the galaxy, instead of what we expect from the visible matter? Because just from the visible matter stops here, so as we go outside, we should see that the velocity will decay. Well, the only other explanation is to say, okay, maybe there is no dark matter, so the mass that we have in our Newton's law of gravity, it's just visible matter. Matter does not increase as we go outside, but then we need to change Newton's law. And one possibility to change Newton's law is basically to say that the gravitational attraction does not decrease with the distance square. Maybe the gravitational attraction decreases in another way. Okay? So this possibility was in fact investigated by Milgrom in 1984. And he proposed a new theory of gravity called modified Newtonian dynamics as an alternative to a dark matter particle. So what Milgrom proposed is something very simple, a phenomenological force law, where it says that the force, the gravitational force, for systems where the acceleration is quite strong, it's just the Newtonian one. So this is the case, for instance, if we are on Earth or in the solar system, the acceleration is quite strong because you have quite a lot of mass, and the force decays is 1 over r squared. But when you go to very large scales, like galaxy scales, cluster scales outside in the universe, the force decays is just 1 over r. And what is surprising is that with this very, very simple modification of gravity, he was able to explain the galaxy rotation curves. So you can see, for instance, for a very specific galaxy, the NGC 1560, if you have the galaxy rotation curves on the y-axis and the distance, the data points, these are these blue points, and you see the modified Newtonian dynamics at the red curve here, it basically follows very well the data points. So there's no dark matter in this red line. There's only visible matter. There are only the protons and electrons that we know the standard model describes very well. But what he did, he basically changed Newton's gravity. If you're going to do Newtonian gravity just with the stars and the gas that you see, you get what we knew was the wrong answer. And what is surprising with this theory of modified gravity is that you can not only just explain how stars move around the galaxy, but many, many other galactic properties that we have. In fact, even better than when you use a dark matter candidate. So in fact, at galactic scales, a modified theory of gravity like MOND explains much, much better galaxy properties than a cold dark matter component and general relativity. Well, but of course, we cannot have two theories to explain the same phenomena. Either Einstein's general relativity is correct, or we need some kind of theory of gravity that gives MOND at these scales. Or we have a dark matter particle. So as physicists, we need to find out which one is the correct answer. And in order to do that, we can look at galaxy clusters. So galaxy clusters, these are big objects in the universe, so it's clusters of galaxies, so many galaxies together. And galaxy clusters are made basically of galaxies, of course, and they also have intergalactic medium gas. So this is just molecules that live in between the space between the galaxies, between the stars, sorry. Okay? So these are the galaxies clusters. Now, if we are going to measure how much matter there is in galaxies in a cluster, only 10% of the total mass of a galaxy cluster is made of galaxies. 90% of the mass of a galaxy cluster is the intergalactic gas. So stars, they basically, you can take out all the stars from a galaxy cluster and the galaxy cluster will still be very massive. It's the intergalactic gas that really makes the mass of the cluster. This is true if there is no such a thing as dark matter, because that's only what is true for the visible matter. That's what we can see. If there is dark matter, then the balance changes completely. The visible matter is only 10% of the galaxy cluster, and 90% of the total mass of the cluster, in fact, is dark matter. So dark matter really dominates galaxies and galaxy clusters, and the universe in general. Normal matter is only 5% of the total universe. It's very little. Okay? So it would be fantastic then, for instance, to look at the galaxy cluster and try to measure how much visible matter there is and how much dark matter there is. If we can measure them, we would know, well, is it really true that there is 90% of dark matter and only 10% of normal matter or not? So how do we measure things? How do we see in astronomy? So galaxies, we can see using telescopes which detect light on the optical range. That's like our eyes. You know, when we look at the universe, we see stars with our eyes. So it means our eyes are good detectors for detecting light at wavelengths, at frequencies, so-called the visible ones. And that's how we see galaxies. So we can take a telescope, look at the optical range, and detect how many galaxies there is in a cluster, and weight all these galaxies together, by basically looking at the stars. The gas, the intergalactic medium gas, we cannot see it with optical telescopes, we need to see it with X-ray telescopes. With X-ray telescopes. And that's why sometimes we call it the X-ray gas. That's the way we see it. So we need an X-ray telescope, usually a satellite, to measure the gas. And then we should have that in the galaxy cluster, so the dark matter. And the dark matter is more difficult to see because it's dark. It doesn't interact with light. So how can we see the dark matter then? Because we'd like to measure how much dark matter there is in the galaxy cluster. Before telling that, I want to remind you again of the numbers. So 10% of the matter should be in the stars, should be optical. X-ray should be about 90%, and that's only if dark matter doesn't exist. Because if dark matter exists, the whole amount of mass in a cluster should be basically dark matter. Very good. So how can we see dark matter if we can't see it? That phenomena, we can use something that is predicted by Einstein's theory of gravity, which is called gravitational lensing. So gravitational lens is a phenomena that comes from Einstein's general relativity, because Einstein's general relativity says that space is curved every time you have a massive object in some region of space. So for instance, if you have the sun will curve space around it. So when you see, for instance, light from the stars, this light of these stars will move towards us, to our telescope, to our eyes, and will be bended because of the curvature of space. So in fact, there's this interesting phenomena, which is when we see the light from a star, we are misplacing the star in its position in the universe, because we always have the feeling that when we see light, it comes from a straight line. So coming from a straight line, the position of the star will be somewhere else, in fact. Okay? So this is something predicted by Einstein's theory of general relativity. And this is something which is not only a prediction, but this is something that now we observe, and we can confirm that this lensing effect really exists. So for instance, if you are on Earth, we have a cluster of galaxies in the universe in the middle, and if you have some galaxies in the background, we have a real galaxy here, the light will come towards us in all these directions, so we will have the feeling that we have a galaxy in a different position there. And this is an example of a picture of the gravitational lensing. So we have a galaxy cluster in the center, and we see these blue arcs there. These are basically images of a galaxy which is in the background. It's the same galaxy, but it's just in the background there. Okay? So for those who don't know general relativity, who are not physicists, you can think of lensing as a phenomenon like when you see an object through water, for instance, through a medium. You will see that there will be a distortion of the object that you see, because light hits that object, goes through the medium, so will change direction, so when you see, you'll see distorted. And this is the same when you look at galaxies in our universe. So if you're on Earth, you have a telescope observing a distant galaxy, the light of this galaxy will travel through the universe and might travel through a galaxy cluster. A galaxy cluster will create curvature in space, and that means your galaxy, which should be all nicely, like it could be a spiral or whatever galaxy, it will look at you completely distorted the image because the light rays are bended. And so this is the method that we can detect dark matter, because even if there's, you can imagine the situation that you have a galaxy in the background, and what you see, even if there's nothing between us and this galaxy, if there's a dark matter particle or halo here, we would see that this galaxy is completely distorted, even if there's nothing here. So the only way to interpret this is because there is, for instance, a dark matter halo in this part. So we have a problem now, which is, okay, let's take a look at a big galaxy cluster in the sky. Try to use the optical telescope to measure how many stars there is in this galaxy cluster, so many galaxies. Then let's take an X-ray telescope to measure what's the amount of intergalactic gas there is, the X-ray gas. to measure. And let's look at the same galaxy cluster now using a lensing method, sleuthing lensing, and looking how light is distorted when it goes through that galaxy cluster to measure how much dark matter there is. The problem is that in a galaxy cluster, everything is mixed together. The stars, the X-ray gas, the dark matter. So then it's very difficult to really do this measurement in a separate way. So it would be very nice if we could separate the stars, the galaxies, and the gas in one place, and then the dark matter into another place. Dark matter always follows the galaxies, because remember galaxies, well, maybe you don't know, but galaxies form in the center of dark matter halos. That's an important information you should know. Okay, but we are human beings, we always think we are very important in the universe, but we're not. We cannot tell a cluster, hey, galaxies and dark matter go to one place and the X-ray gas goes to another one. We cannot do that. But what we can do is to wait for the universe, for some phenomena to happen, in particular, the collision of clusters. So what happens when clusters collide in our universe? What happens is the following, and this is just a numerical simulation of two clusters, the small one and the larger one. So blue will be representing the galaxies and the dark matter around the galaxies in there, and red will be the X-ray gas. So when clusters collide, you have this kind of phenomena, that both the galaxies and the X-rays, they are merged together, and as the cluster collide, one goes through the other, and you'll see that something quite interesting happens, which is the galaxies, or the dark matter, these are collisionless particles, they seem to be moving faster than the X-ray gas. So the X-ray gas seems to drag behind and doesn't move so fast in a galaxy cluster merger. So this is quite interesting because at the end of a cluster merger, we have that the galaxies, or the dark matter, that's the blue part, collisionless particles, they just go through each other. So they move very fast. And in the center, the gas drag behind. And the reason is because the gas is made also of charged particles, so they interact electromagnetically with charges. So they have something called ram pressure. So basically, it's like some kind of friction, and so they move slower through each other. While galaxies, or the dark matter halos, they are basically collisionless particles. So they just go through each other, they don't feel each other. So they move really, really fast. So now we are in a quite interesting situation because now we have a system where we have managed to separate the X-ray gas from the galaxies. And remember, if there is no dark matter in the universe, most of the mass should be on the X-ray because only 10% of the mass of the cluster should be in the galaxies. So that's going to be the blue part. And 90% should be in the X-ray gas, if there is no dark matter particle. So that means on that system, if I'm now going to do a lensing analysis, so if I'm going to look at this system and we have some galaxies in the background, and I'm trying to try to find the light from those galaxies in the background will go through these clusters. So where does the light, the image get more distorted? Where does the lensing is stronger? Where is the bending of light stronger? I should see that since most of the mass is in the X-ray gas, light should be distorted very strongly here in the center of this collision of the clusters. And the lensing here should be very small because most of the mass is here. So here, there's a huge curvature in space in the center. There's the curvature of space should be very large here and very small there. Very good. So in 2006, some astronomers in Harvard, they looked at a system of clusters that have collided several billions of years ago in the universe. It's called the bullet cluster. So this system, they say, wow, this is an ideal system to try to do this lensing analysis, looking at the gas, looking at the stars, and see if there is dark matter there or not. So first they took a picture with the Hubble Space Telescope in the optical regime. And this is the picture that they took. So this is one cluster. So you see there's more galaxies here. And then there's quite empty space. And then there's another big cluster here. So this small cluster basically is the bullet. It's a small cluster that went through a very big cluster, this one. So the bullet cluster end up there. And the big cluster is here. Okay? And so, and we can measure the velocity of this galaxy. They are all moving in that direction, while these ones, they are moving in this direction, in there. So we know that these clusters really collided several billion years ago. So they took, with the Hubble Space Telescope, they took this optical image, and now we know how many stars, how many galaxies there are in this cluster. And then they went to the Chandra telescope, is a satellite, whose aim has a detector which only for X-ray light. And they went to take a picture of the same system, but now with the X-ray light, X-ray radiation only, with the telescopes. And what they see, the system is very dark here, but in there, in the center, where there's nothing here in terms of light, there's a lot of X-ray gas. Yes? So we see this is the same place, so all the bullet cluster, all these galaxies should be more or less there, and all these galaxies should be there. But the X-ray does not see. This detector only sees the X-ray frequency. Yeah, band, let's call it. You know? So this is, wow, this is precisely what we would like to do. And let's do a lensing analysis in this system to see whether light from galaxies in the background are strongly banded here, where the X-ray is, in the middle, or whether the lensing is more banded there. If there's no dark matter, most bending of light, the strongest curvatures of space should be in the middle, where we don't see any galaxies. However, remember, if there is dark matter is these big halos where galaxies are in the center, and dark matter is also collisionless. And so, if there is dark matter in the universe, when I do a lensing analysis, I should see that most of the curvature of the universe should be here, outside the X-ray. This is where the big curvature should be, because that's where dark matter is. So they put together the two images. Now we see the galaxies there, the galaxies here, and that's where the X-ray gas is. And you can even see that the gas is also moving in this direction. You can see this shape of the gas moving in this direction, and that gas is moving in that direction. So it's really a collision of two clusters. So that's the optical and the X-ray images overlapping. And now they did the lensing analysis. So they look now at galaxies which are on the background of these clusters, behind these clusters, and see what happened to that light. And what they saw, so there's the galaxies, that's the X-rays, of course, and this is what they saw. So I'll look here because it's a bit cleaner. So these green lines, they represent what is called the lensing contour plots. So it means that the lensing is very strong in the center of these lines and becomes very weak as we come to the outside. So you can see clear from this image, the lensing very strong here where there is no gas, and very strong there where there is no gas. And it fits perfectly where we have the galaxies here. It fits perfectly where we have the galaxies there. So the stronger distortions of light, they're coming from these regions where, precisely where the galaxies are. So the strongest curvatures in space, they come from the galaxies, they do not come from the gas. And that means that there must be some mass here on the galaxies that we cannot see. Some mass that's really creating these huge curvatures in space-time that is making light to bend. And so this analysis, this article, in fact, the title is An Indirect Evidence for the Existence of Dark Matter, because this shows that there must be some dark matter particle which create halos around galaxies, and this dark matter particle must be very heavy, very massive. It dominates completely galaxy clusters because the X-ray gas should represent, they are 19% of the whole normal matter there is in the galaxy cluster, the baryonic matter, as we call it, cosmologists. But in fact, most of the lens in the big curvatures is not there on the X-ray gas. So this puzzle, is it dark matter or modified theory of gravity like Milgrom proposed? Well, the answer for that, it seems to be a dark matter particle, most probably because of this observation. So it must be a very massive particle, but that does not interact electromagnetically. So it doesn't interact with light because we cannot see it. It's just there. Now, how do we find this something that we don't see? Well, what people do is that maybe it's very difficult. Well, maybe we have already found it via gravitational effects. That's what it is. But we hope as well to find this dark matter particle looking at particle physics experiments in, for instance, in CERN or in the Fermi Lab. So these are laboratories in Europe or in the US. And we've been trying to find this particle now for several decades, in fact. And people are, in fact, getting a bit desperate because it has been more than, I think, 5 decades, 50 years that people have been doing these experiments, particle physics experiments, either direct probes or even indirectly, and up to now, nobody has managed to detect these dark matter particles. So that's a very big mystery of the universe still. Most of the community believes that dark matter should be a particle, but science is not about believing, it's about scientific evidence, experiments, and so it's still an open question. Okay, thank you very much.
Yes, thank you for the very nice one. So I was just curious that is there what is the ratio of the galaxy radius and the dark matter halo radius, and is they have some fixed ratio?
If it is, sorry, I didn't understand.
What is the ratio of the dark matter galaxy radius and the dark matter halo radius? And do they follow some fixed ratio?
Yeah, very, very good question. Yes, the dark matter halos, that can be very big. They can be up to, okay, since we can't see them, it's all based on simulations and what we see with lensing observations. So it's very difficult really to put a number on there. But simulations indicate they can be 10 to the 14 solar masses. So as I said, like a galaxy is about kiloparsec, so thousands of parsec. Megaparsec is like 1,000 times larger. So the radius of a dark matter halo can be at least 1,000 times larger than a galaxy, or even more sometimes. So it can be really, really big, the dark matter halo. Yeah.
Okay, for the more thank you for the viewing presentation. So I have like a couple of questions for me. The first one is about the rotational curve. I have question that with the r equals to 0, why the velocity loss of is not equal to infinity, something like that.
Sorry, what did you in the?
Rotational curve.
Yes, let me see. This one?
Yeah, where the distance is like at the center of the galaxy, where the observed rotational velocity is becomes zero?
Oh, well, no, it's just, because you set up like the supermassive black hole, like being, of course it's moving, but within the reference frame of the galaxy, we just said that's the center, so it doesn't move, it's the supermassive black hole, and then you start measuring the velocity of the different galaxies from there. That's why it goes to zero, but of course, that's just a theoretical curve. The data, usually the data start much larger. Let me see if I have the data. Yeah. On the, let me show you. Well, the data points, yes, they don't really go to zero. They go here, somewhere there. So we cannot really measure the center of the galaxy. Yeah. Sorry.
Of the velocity, right?
The peak there?
Yeah, it can be on the both graph, but actually, like F is proportional. It must be proportional to the R square, right? So if R is increased, or the velocity should be decreased.
Oh, you mean decreasing since the beginning?
Yeah.
Yeah, but there's a lot of mass here, so it's like you can imagine if I have objects in my table, and I rotate the table from there, and I rotate the whole table. All these objects move basically at the same angular velocity, but this one even rotates faster than this one at the center. I don't know. So if I have this screen, and I have this laptop, I rotate the whole table around me. Yes? So this object, in fact, here moves slower because the distance is smaller for the same time than that one. So in the galaxy, since there is so much mass all over in this place, in fact, this galaxy or this star will move faster than the one in front. And then at some point, the mass really decreases, and then you should see really a decay. I don't know if that was your question. I think your question, why does it grow, and then why it decays, yes?
I think the question is about the force.
Oh, to this part? No, well, usually the force is more applicable to that part. Yes, that we see but we should, the reason why I'm showing the force is that because you should expect the decay afterwards, because the mass is smaller and smaller. You have to speak, I can't hear you.
So your answer is mean that you cannot expect just like it has only one source for the velocity. Yeah, so there are many sources from another source that like
Inside the text. Inside the text.
Inside, that's a galaxy?
Some
other source.
Either
only just that. There might be some other forces, not only just the force obey powers of the.
No, well, this is a very simplified formula, of course. No, it's huge. It's very complicated. This is a public talk. The process is much more complicated than I'm showing here, of course. No, just to give an example, to give an intuition what could be the dark matter. No, this is a public talk. We can talk about details later.
And another question is on the bullet cluster.
Yes? Yeah. On the simulation or in the...
What is the blue color means? Does that mean dark matter?
Yes, so the blue color here means the galaxies. That's what I meant. So the red is where the gas is. Gas is going to be in the middle. And the blue represents the dark matter particles or the galaxies. Those are collisionless particles, so there's no friction when they go through each other. They don't feel each other, so you just go through. That's what I meant.
Dark matter cannot like interacting with your EM field, something like that. So why you can like why can you draw the regions of dark matter exactly like this?
These ones, the lensing? These regions there, the lensing contour? It's because we use lensing. So
The blue color. how can you know that dark matter is there?
No, the the blue color is just a picture here. So the real images, what we really see, we only see this. The X-ray, that's a real observer, and we see that part. So that's the X-ray, and that's the optical light. So when I put blue here, is just to represent where the galaxies are. So this is not a real image, this blue thing here. I'm just putting where the galaxies are, and then I do the lensing analysis there.
So the blue colors doesn't mean the actual dark matter region.
No, it does not. Well, it does not because, but what we know is that galaxies form inside dark matter halos. So if you have a galaxy, the galaxy formation theories, they all come that if there is a galaxy, it means there is a dark matter halo around. It's very rare to find galaxies in voids, for instance. There are some, but it's very rare. So if there is a galaxy, there's a dark matter halo. And that's why if there's a galaxy, we just painted this part a little bit blue. But that's just, again, this is a public talk just for visualization purpose. But what we see is just this. We don't see anything. We just see galaxies. And then when we do the lensing, we see this is a very strong lensing. Images of the background galaxy get really distorted. So much distorted that they shouldn't. They should be distorted where the X-ray gas is. This is what happened, yeah.
Okay, that's all for me.
Thank you.
There is something I'm really confused about, like the gravitational lensing. Like, I think like the light has time to move to the Earth, right? And also it has the same speed as the gravitational wave. That's what I understand. And then if I imagine like the light coming from the background, like background star, for example, and it's moved around the galaxy, and then you observe it, right? But the galaxy you observe is there in the past, so it's and the distance of that light that's coming to us is shorter than the light that is moving across like these galaxies. So how do we know that? Like it's about the time, yeah. The time of that galaxy may be different from the time when we use the gravitational lensing.
No, we don't need to know the time. So we have here, for instance, what we know is that we see this. So this one is that one here in the center. Yes. Okay, and we just see this image. But what we see is that there is this image, is light coming from the edges, and when we do spectroscopy, because the first question, how do we know this galaxy is in the background? That's the first question, yeah? Okay, and the way we do it, we can do spectroscopy, so it means we can calculate what redshift this light comes from. And we see this redshift is different from this one. This one is closer to us, lower redshift, than this one, the light one. And then the second question you can ask, how do you know this image is the same as that one? You know, like this galaxy that we see in this direction is the same as that one. Because we do spectroscopy, again, we analyze the light composition of these lights, so we can calculate what are the chemical elements that have emitted this light here, and we see it's the same as these ones, and that one, and that ones, and that ones. So then we confirm this light come here, these images of these galaxies that we see, is they basically the same galaxy that is in the background of that one. So I'm not sure if we need to know the time. So I'm not sure if you...
We compare the results with the X-ray, and we compare the result from the X-ray and the gravitational lensing, right? How do I know that it has the same time, like the same distance? So it's mean the same time when it comes to the speed of light. Yeah.
Well, we don't need, so this phenomenon, so just to give an idea, this was in 2006. if you look it again 20 years after, you see the same things. So the universe takes it takes a very long time. So the time here doesn't play a role. If I go now and I find the James Webb Telescope, take another picture, Chandra take another picture, doing a lensing analysis, everything looks the same. Galaxies take a huge amount of time to travel through our universe. So time is not important. What we need to know is that you know where is this gas, so you calculate the redshift that the gas is, so when this gas is, at what redshift it is, it's very close to us. This light comes from galaxies which are several billions of years or redshifts away from us. It's really a background galaxy. And we know that because when you do the lensing analysis, you see the light bending, but you can also get the composition of this light. So what is the chemical composition of those galaxies?
Yeah, but that assumes that like there's nothing in between, like the galaxy and us, and also that galaxy and the background star. Right?
Oh no, there will be. There is for sure. That's why this was only done in 2006, because the whole analysis is very complicated. The whole data analysis, cleaning up all the so-called foregrounds, because there are clusters in front of us, there are clusters behind those galaxies. It's a very complicated analysis. So they need to really pick up, like that they are seeing the right photons coming from the right places. And it's a mess. When you put a telescope up there, you get everything, So it's a very complicated analysis to be done. That's why, otherwise people would have done that a long time ago.
Yeah. So you have a slice of like the layer of different time, different space, different distance. That's what I mean.
Yes. So when we look at the universe, you look at one of these stars or galaxies. You analyze the light. You can analyze the amplitude of the light. So it's very far or very close. Okay, that's just luminosity distance. But you can also measure the redshift, so the frequency of the light. And the frequency of the light basically can tell you, usually it's just not one photon, it's many lights. So it gives you different, I don't know if you know what is spectroscopy. Yeah. So basically you can do spectroscopy. So you know what is the composition of, for instance, you find it's hydrogen in this light. So you see the spectral lines of hydrogen, and you see they are all shifted by redshift, let's say 2. So it means that this object is at redshift 2. It's on the background. This one, for instance, closer by is at redshift 1, because you also do a spectral analysis. So it means that one is behind and the other one is in front. So, and that's why using the redshift, you can do slices in time in our universe.
And you mentioned both from the optical lensing and from the gravitational lensing and the X-ray.
Yes. Yeah. You measure you can do spectroscopy on these different from the optical on the X-rays. It's even more complicated than that. But yeah. But yes, you can do it. Yes.
Okay, so you mentioned about Mount. This part is something phenomenological, right? Just to try to match with the observations. But do you know about any modified gravity theory that explains expansion as well as this phenomena at the same time, like recovering Mount instead of Poisson equation? Do you know something about that?
Yes. So there are, so of course, Mond, none of the physicists here would start believing in Mond instead of general relativity, yes? Because not a relativistic, not a covariant theory. So people have been working on relativistic versions of Mond, so relativistic theories of gravity, where in the limit, they get Newtonian gravity when you come to the Wakefield limit on solar system, for instance, but they get Mond at galaxy scales. And a very famous one is the Bekenstein-Tevez, a tensor vector scalar theory of gravity. So you were in my lecture, so you should know that besides having the graviton, you also have a vector field and a scalar field. And that theory can explain both the background expansion, it has a Newtonian limit, is relativistic. can explain the lensing, but has problems to explain the bullet cluster, for instance. You know, and nowadays there's another theory called chronon, and then there's another theory called ether. So these are a bit better versions of theories, fully relativistic theories, just like general relativity. They have usually more. They are more complicated because they have scalar fields and vector fields involved in those theories, and they can be an alternative to dark matter. And they have shown to be explained very well all the background expansion of the universe, all the large-scale structures like cosmic microwave background radiation, the linear power spectra, and all the galaxy phenomenology because they have a Mond regime. And now people are testing them in clusters. So they are testing these series to see if they can explain the bullet cluster observation. So that's the final test. But all the other tests, they passed it very well. So there are these promising theories, but they still need to, someone needs to write an article to explain the bullet cluster observations with them, and they are doing that. They are doing that, yeah.
Just my last question. So, do you believe that we already have a strong evidence to expect to find this particle in the same way before they were expecting to find the planet and they found it? Now, what's your opinion?
I think in the beginning I was like, if you asked me 20 years ago, I say yes, I think we'll find the particle in the LHC. You know, it's just a question of time. We increase the energy of the LHC, so we'll find it. Well, we have been doing this for 50 years now, so maybe we have to wait. You know, the universe is very old, so maybe we just have to wait another 100 years, or I don't know, to find the particle. But it's getting a bit strange, I think. Like the usual supersymmetric models for dark matter, the parameter space is becoming very, very small, like really shrinking. So maybe there are some other candidates from dark matter, which there are, of course. Theoretical physicists, we have a lot of imagination, so we can do that. But it's getting very problematic. So that's why I think people, when Mond appeared, people were very skeptical, but nowadays people are coming back to these possibilities of these theories of gravity which have a Mond regime in certain scales. So I think people are now coming back to that because they've been waiting for this dark matter particle to be detected and we haven't seen it. But well, the good thing about science is science doesn't care about my opinion or yours, you know. Science and the universe, you just have to work on things. And I think 90% or 99% of the things you work, they won't lead anywhere. And maybe there's 1% of chance that you get it there. But yeah, so we just need to keep working on this. Yeah.
Okay, I guess there is no further question. I would like to thank you, Professor David Mota, for giving us an insightful talk today. And please thank you for the speaker. Thank you. Before we go, I would like to invite